1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学的数学原理》。1736年，欧拉走过哥尼斯堡七桥，并开创图论这门新的学科。20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和香农定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高空推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。链接实践和整合资源，积极探索和开拓创新，讨论碰撞和相互激发。
Okay, so hello everyone. Good morning, good afternoon, good evening. Welcome to the TaskPark course series on fundamentals of channel knowledge map from classical to AI-based methods. This event is organized by TaskPark, which is an open platform dedicated to fostering academic exchange by connecting researchers, scholars, and professionals across different cutting-edge disciplines. So my name is Jie Xu from the Chinese University, Hong Kong at Shenzhen. So today we're gonna have the fourth lecture on CKM construction, delivered by Professor Chen Junting. So in this part, he's gonna talk about blind construction and the environment-aware CKM construction approaches. So before we start, let me give a brief introduction about Professor Chen. So Professor Chen is currently an assistant professor with the School of Science and Engineering and the Future Network of Intelligence Institute at the Chinese University of Hong Kong, Shenzhen. Dr. Chen received a bachelor degree from Nanjing University in 2009 and a PhD degree from the Hong Kong University of Science and Technology in 2015. Prior to joining CHK Shenzhen, he was a postdoc research associate with University of South California and also with the Department of Communication Systems, Eurocom, in France. His research focuses on signal processing, optimization, and machine learning for radio map construction and exploitation in wireless communications and localization. He is currently serving as editor for IEEE transactions on wireless communications. He was named as examiner reviewer for IEEE wireless communication letters. He received the Charles Hall Best Paper Award in 2022 Wireless and Optical Communication Conference. He is also the workshop co-chair for ICCC workshop on channel knowledge map. Without further ado, let's welcome Professor Chen to give us a talk. Professor Chen, the Stage is yours.
All right, thank you very much for the very nice introduction. So so is my screen sharing was well?
Yeah, continue.
Okay, good. Yeah, hello everyone. So welcome to lecture 2.4, which is about blind construction and environment-aware CKM construction approaches. So in the previous lecture, we've talked about several typical approaches for CKM construction. So let's just have a very quick review of those typical principles for the construction. So recall that CKM is a mapping from the transmitter or receiver location to the channel knowledge, Y, where Y could be any CSI information that we are interested in, for example, the received signal strength, delay, angle, etc. And then through this mapping, and of course, the environment plays a very important role. So the CKM construction is typically to learn a mapping from the location to the channel knowledge. So in the previous lectures by Professor Zheng Yong and Professor Xu Jie and also me, we talked about several classical methodologies, including model-assisted approaches, where if we know the environment, right, the geometry on the environment, we can launch those rays. We use a ray tracing approach to launch the propagation ray, and then we can use propagation theory to estimate the channel from the receiver from the transmitter to the receiver by examining every possible propagation paths, so that we can end up with the information of the angle and also delay. And of course, this is not the end, right? Because the approach relies on precise information of the 3D environment as well as the electromagnetic characteristic of the material in the environment. So in practice, we probably need some measurement data to calibrate the model. Right, so this is model-assisted approach, and then we also have machine learning approach, right? So we talk about interpolation or maybe matrix tensor complexion approach to learn this mapping based on a large amount of data set, which gives us some location-labeled CSI data. We also talk about deep learning approaches, where we instead using a physics-inspired model or some data-driven model, we use a deep learning model to learn such a mapping. Now here's the challenge. First of all, we need to collect a large amount of data, Zi, Yi, where Z is the location, right? So we need location label data. And this also leads to the subsequent two challenges. One is the possible model mismatch. So as I mentioned that when we use model-assisted approach, we need to know the environment, and that information may not be accurate enough. And in addition, the environment could be changing, right? Because for the indoor scenario, we probably could move the router, we replace the router to a different location, or we may move the furniture in the indoor environment. Then the propagation environment is changed. And for an outdoor, we may have a different traffic scenario. We may have a truck that block the antenna, right? So the wireless scenario could change. So this implies that we actually need continuous calibration using a large amount of location label measurement data to keep the radio map up to date, especially when the environment is time varying. So the fundamental challenge is how to get the location, right? If we talk about the real applications. Now, in a station approach, people talk about the acquisition of location information using probably some third-party methods. For example, we can use GPS, or we can use camera, or we can use ultra wideband localization to get the location information. No matter what method we use, we need to have some additional resources. For example, we need additional hardware. We also need the software implementation to synchronize the GPS data with the wireless communication, right? Which is usually very challenging, because if you work on GPS, you will know that the GPS refreshing rate is at the order of maybe 100 milliseconds or much longer. But then for wireless communication, you probably need to acquire the channel information at the time scale of 10 milliseconds. So this also increased the challenge for deliver service to dedicated users because of the issue of the mismatch time scale from the GPS location and the requirement of the CSI update. There are actually more issues when explicit location is required. For example, the freshness of the data, right? That is something we have mentioned about. So if we use GPS, there's some latency. If you use camera, we also need to run some sophisticated algorithm to extract the location information through processing the image data, and also reliability. And this also leads to the privacy concern. If we talk about using a crowdsourcing approach to collect location labeled data from a large amount of mobile users, then this implies that the user need to report the real-time location to a fusion center. Then this can impose a serious privacy issue. People may not want to disclose their location. Then if we don't resolve this issue, we may not motivate the crowdsourcing approach for a large amount of the data collection. And lastly, as we mentioned before, as the environment is changing, we need to collect a large amount of up-to-date data in a maybe daily or weekly basis. So this leads to a concept of self-localizing radio mapping. By self-localizing, we imagine that while we collect the data, which is without location label, and we can somehow recover the location label of the data. And so we have a location label data set to help us to construct a radio map or update the radio map, right? So this is just one possibility that we would like to focus on in tonight's lecture. So now, of course, if we just have a very few amount of data, it is very difficult to do that. But imagine that we are given a huge amount of data. So just imagine we have a router that keep listening to the communication of a bunch of mobile device, although it does not know the location of those mobile devices, but it can like collect those CSI data. And as time goes on, it can accumulate a large amount of data. So our problem is, if we are given, if we have observed enough amount of data, can we discover the hidden structure of this data to recover the location? So this is from the perspective of blind radio map construction or self-localizing radio map construction. So when we come to the utilization of radio map, right? We also have the issue of how we know the location at the first place. So in a conventional communication structure, the system does not need to know the location of the user in order to perform beamforming, right? So this is what a conventional approach would do. We have the CSI, we have the channel, and then the system will launch some probing signal to try to estimate the channel. And then based on the channel estimation, we can do some beamforming extension. Now with radio map, A conventional approach would need to also input the location label to the radial map so that the radial map can read out the corresponding CSI by pairing the location with the CSI in the database. However, if we do not have those location, then we need to think about how we still make use of the historical CSI, meaning radial map, without the location label, right? So this gives us a new structure of the system where we still keep the conventional signal protocol, but now we have a new database that record all the historical CSI as radial map, and then how do we utilize this database to enhance the CSI estimation or beam tracking performance. So now here's the outline. We'll go through four topics. First, we will talk about some straightforward generative approach and also a channel charting approach. Then we'll go to the theory part, try to investigate why is it possible to recover the location label from a large amount of unlabeled CSI data. And in particular, we'll find out the so-called fundamental limits from an information theory perspective. So if you work on some engineering problem or you are a practitioner, you probably can skip this part and come back 10 to 15 minutes later. But if you are working on information theory or signal processing, then you may find some interesting idea there because we just will go over some methodology that we use to study those fundamental limits. And then we'll talk about two tools for us to recover the location labels. One is to use the Bayesian trajectory recovery framework that exploit the temporal correlation from the measurement data. The other one is to use the so-called spatial regularization approach that try to exploit the spatial correlation of the amount of CSI data. Okay, so generative approaches. So this is quite straightforward. Imagine that we have trained a neural network model where the model input the geographical map along with possibly some RSS measurements, which is highly optional. Then the deep network could be trained to map the environment directly to the CSI, right? So there are a lot of state-of-the-art works focus on this direction, including using GAN or using diffusion or maybe even using large language model to do that. So in our other lecture, we also talk about those generative approach to generate the CKM. So we will not go into the detail of this approach. I just try to give you the rough idea. This is possible if you don't care about if your goal is not to achieve a very high precision of the CKM, then generated approach would be the first method you would like to try. Now the other one is called channel charting, which has been around for many years. So the idea is the following. So let's say we observe a large amount of CSI data, and imagine that the CSI data has high dimensional. Now, for example, we have a large bandwidth. Then we can we observe, if we use OFDM system, we observe the channel from a large amount of subcarrier. And then if you have multiple antennas, so I would have a high dimensional CSI that represent the subcarrier state for each of the antenna. So the CSI is high dimensional. However, the underlying the the physics is low dimensional, right? Because the mobile can only move along a 2D space, although the CSI is in high dimensional, right? So this naturally leads to a so-called multi-dimensional scaling problem, where we try to embed the high dimensional CSI to a low dimensional physical space. And the typical formulation to do that is try to minimize this cost, where yi and yj are the CSI measured at location I and location j. And here, where under unknown locations, right? So we try to recover the location xi and xj such that if the distance between the two CSI y and yj is more, then the distance between the two locations xi and xj is also small. So which means that we try to learn, we try to recover those locations such that a smaller CSI distance will imply a small geographic distance. On the other hand, a large geographic distance probably, a large CSI distance probably imply a large geographic distance. So this is the essential idea, and then people come up with a bunch of different metrics to measure how close to CSI is, right? Because CSI lies in a high dimensional space, which may not be a Euclidean space, maybe a manifold can better describe this space. So a hot research topic is to try to investigate better CSI distance measurements to specify this objective. And also, since this problem is sophisticated and the CSI distance to the geographic distance relation may not be linear, so there's also another research topic that try to develop a better deep learning framework to perform to perform such a CSI embedding. However, this method also needs some precise location label to correct the so-called translation, rotation, scaling of the embedding. Now, in our next topic, we'll try to go deeper in the theory to try to understand from a physical point of view why it is possible to recover the location labels from the large amount of CSI data. The fundamental concept or principle would be quite similar to the channel charting, where we try to embed the high dimensional CSI to a low dimensional physical space. But we try to view this whole objective from a model-based perspective and try to come up with some interpretation on why it should work. So the principle is quite straightforward. We observe a large amount of unlabeled CSI data, and then we try to somehow recover the location label so that we can pair the location with the CSI statistics to construct a radial map. Now here is an outdoor example to give you a rough idea why it should work. So this is a city map where we have a few street blocks, and then we have a few base stations. For example, base station 1 here, base station 2, base station 3. And these colors trajectory represent the trajectory of a mobile. For example, we have a yellow trajectory that moves from base station 1 and then gradually towards base station 2. And then we have another trajectory that starts from here, passing base station 6, and then base station 2, and then base station 1, so on and so forth. Now, you can imagine that a straightforward signal characteristic is as I move closer to one base station, the signal strength from that base station becomes stronger. And if I go further away, then the signal becomes weak. So if we look at just one trajectory, we can imagine that the signal from base station 1 first becomes stronger and then become weaker. So this would give us some side information that at some point I'm closer to base station 1, and then at the other point I'm closer to base station 2. So that means In terms of the CSI, if I take the CSI in sequence, I take a sequential measurement of the CSI, then by examining the signal fluctuation, I can somehow pinpoint where I am. So this is the fundamental idea. So here you may wonder, then what is the difference between localization and trajectory recovery? And here we make a comparison. A conventional point localization will focus on the localizing just a particular point. So say my location is here, then I probably see base station 1 in line of sight, but then base station 2 in non-line of sight. Now, if I'm blocked by some obstacle, then the localization performance will be very poor, and we have nothing to do with that because the blockages induce a bias. We cannot take multiple measurements to eliminate those bias. Now, trajectory recovery is slightly different, or batch recovery is slightly different. What we are focusing on recover the trajectory as a whole. We do not care about the point-by-point localization performance. So this is one point. The second point is that those measurements are highly correlated in time and also in space. So that means we can exploit the so-called temporal and spatial correlation among those measurements so that different adjacent measurements can help each other to correct the localization, to enhance the localization performance. In addition, we can also utilize some sign information, for example, the street map and also the base station locations to enhance the localization performance. So this is a fundamental difference between point localization and trajectory recovery or batch recovery. Now, let's go deeper to argue why it is possible to recover the trajectory. So there are mainly 2 points. One is that there exist non-parametric localization techniques. The idea is somehow I have illustrated before. The closer to an anchor, you will receive stronger signal from that anchor. And that naturally leads to localization algorithm called weighted centroid localization. So the idea is quite straightforward. Say we have 2 sources indicated by this cross, and then we have a bunch of anchors indicated by these color points. So the look at the signal model and the measurement model, we can form, now if we have multiple antenna, we can form a MIMO beam model. A MIMO beam refers to the case where we can beam from the signal towards a specific direction. Now, for example, say we can form a beam that points to this direction, C. Then we can construct a model where if I deviate from this direction, then the response is weaker. So if I close to this direction, the response is stronger. So just like this. And then this model can equipped with some parameter. For example, this C control the beam direction, the eta control the beam width, and then the omega can control the beam gain, right? So we can leave this parameter unknown and to be estimated. Now we can also make use of the path loss model, where the resistance strength for a particular beam depends on the propagation distance between the base station OQ and the measurement location XT, which is something we need to estimate, and also the response of the beam, where the response of the beam depends on the beam direction, which is something to be estimated, as well as the direction between the position XT, which is something to be estimated, and the position of the base station, which is known. And we also need a mobility model, right? Because as we mentioned, we need to exploit the spatial correlation. Now, in our analysis, we are interested in the case where we move along a rectilinear trajectory, where we have just 2 parameters in 4 dimensions to estimate. So here we are interested in the fundamental limit. So we study the Fisher information matrix. So if you are new to estimation theory, then I can simply tell you that if we are interested in the Fisher information matrix, because the trace inverse of the Fisher information matrix gives us the so-called Craméral lower bound. A Craméral lower bound gives the lower bound of the unbiased estimator of this parameter, right? So this may not be the actual performance we achieve in reality, but this gives us performance indicator of ideally how good we can do in fundamental limit. So here we found that the Fisher information matrix on the initial position x and the velocity v that are to be estimated is given by this formula. And then we can immediately tell that the more measurement we have, t, the more information we have, which translates to a better performance on estimating the initial position x and the velocity v, right? The reason is that this matrix is positively semi-definite. So the more copy of this matrix, the better, the more information we have. Another important information is that the performance also depends on the topology, where LQ refers to the direction from the base station at OQ to the initial position X. So we prefer so by examining this formula, we'll find that we'll prefer the base station to scatter around the initial position of X. That will give us a stronger Fisher information. Then, of course, the SNR also play a role, where alpha is the signal strength, and then sigma is the noise. Now, let's examine 32 scenario. In the first scenario, we consider the case where we have a finitely many base stations, which are deployed in a limited region. But then we allow to take infinite measurements at infinite measurement range. So that means no matter how far you are away from the base station, you can always measure the signal of the base from the base station, although the signal can be weaker and weaker as you move further and further away. Now, however, it finds that although we allow infinite measurement range and we allow infinitely many measurement numbers, t, then the CRLB cannot decrease to 0. The CRLB will converge to non-zero constants, even though the number of measurements tends to infinity, right? So this is a little bit counterintuitive because, first of all, we allow infinite measurements. We allow to travel to infinite far away without, we allow to travel to infinitely far away. And then we only travel along a rectilinear trajectory where we just have 2 parameters to estimate. However, it turns out that we cannot perfectly recover the trajectory. And the reason is that as we move further away, the additional Fisher information we get is decreasing more. So let's look at the second scenario where we have an infinite base station deployment, but then we only allow a limited measurement range. So which means that we can take measurement with the base station only when we are within a radius of r in the base station coverage. But then we allow to communicate with infinitely many base stations. So so you can imagine this phenomenon as you are traveling along a highway, and then at some position you can communicate to base station 1, and then at the next position you communicate with base station 2. Right. So in this case, the good news is now the Craméral lower bound can converge to 0. So the result says that if I examine the product T, which is the number of measurements, and the CRLB, then this product converge to some constant depending on the SNR, the measurement range R, etc. So this is for the performance of recover the initial location. So if we want to recover the velocity, then the expression is like this. So the information, the essential message is that the CRLB for x will decreases like 1 over t, where t is the number of measurements, and the CRLB for the velocity, given we have a perfect position estimate, the CRLB of the velocity will decrease as 1 over t cube, t to the power 3. So now finally, we can perfectly recover the simplest trajectory, which is rectilinear. Now, if we have multiple antennas, we can also gain additional from the multiple antennas, right? By NT to the cube in decreasing the CRLB, where NT is the number of the antennas. So if we have in scenario 2, if we have infinitely many base stations, now we will have also NT to the cube in the band. And in this case, again, we can decrease the CRLB to 0 as the number of measurement t tends to infinity. So the key message is that the more measurements we have and the longer observation we have, the better the recovery, right? So this is the some good results we can expect. So so this is about the theory part. Now, of course, this just focus on sequential measurement. We will look at what we can do in algorithm design. So these results provides us Bayesian approach to recover the trajectory. Say we are given a sequential measurements, and we can first form a measurement model, which is a conditional probability of the measurement yt given the location xt, where the location xt is something we want to estimate. And this theta p is the propagation parameter, right? For example, given xt, we can use this signal model to formulate the observation due to the propagation distance, due to the beam gain, etc. So we have this conditional probability. And then we also construct the mobility model, right? In our analysis, we simply use a rectilinear model, which just have 2 parameters. But in reality, we can have a bunch of model to use. For example, we can use Gauss Markov model, which looks like a random walk, but it is highly correlated. We can also use a random waypoint model. This is more this is closer to the reality. But then if we have the strip map information, we can also use the map guided mobility model to force the trajectory to travel along the streets. So as you can imagine, that the stronger the model, the better performance is better. Now, using conditional probability, then we can form a joint probability distribution for all the measurements and all the trajectory to be estimated. So we get a joint probability expression based on the Bayes rule. And then we can extract or estimate the trajectory x of t that represent all the position for all t time steps, all the propagation parameters, and all the mobility parameters by maximizing this joint probability, right? Which turns out to be formulated into this form. So the remaining challenge would be how to solve this problem easily. So it can actually be solved by dynamic programming or extended Kalman filtering with alternating optimization by alternating between trajectory recovery and parameter estimation for the measurement model and the mobility model. So I'm not going into the detail, but just try to instead we just try to discuss a high-level idea. And now I will give you some specific application example on how to apply this concept to reality. Now, the first application is to do region-based localization. So here in this experiment, we have an indoor environment, which is a pretty large open office area. And then we have 10 regions. The formation of this region is due to the layout and also due to the function of this layout. So this comes from an application where the people want to know the position of the people and the position of the equipment, but up to the level of which room the equipment locates in or which room the people is, right? However, we only have very coarse measurement data. We only have the resistance strength data. So the layout is the following. So we have deployed 21 Wi-Fi sensors in the room, and then those sensors can only measure the resistance strength. And then we try to build a fingerprint map to perform fingerprint localization, right? So as you may know, that to construct a fingerprint map, we need location labeled CSI data. So in this project, we look at whether how can we construct the fingerprint map without the location label data. So what we do is that we employ a measurement trajectory that go through all the 10 regions without repetition. The trajectory is unknown, it's completely random. What is known is that it travels along 10 rooms without repetition. And then when the people enter the room or when it leaves the room is also unknown. So then we can use the previous framework to formulate a Bayesian estimation problem where we estimate the timing that enters a room and the timing that leaves the room. So this ends up with estimation of only 10 variables. Now with that, it turns out that we can fully reconstruct the timing that enters a room or leaves a room. Now, with the timing, we can collect all the measurements within a room and then construct a radial map model, which is called the region-based radial map, to map the room number and the CSI statistics if a mobile locates in that room. So we build the so-called region-based radial map. Now we can use this region-based radial map to perform fingerprint localization. And it turns out that it works pretty well. The experiment is done as follows. So we have 3 days. In the first day, we collect training data. And the second day and the third day, we perform the testing. It turns out that the proposed method works very well. The localization error is just around 0.5 meter. It works even better than supervised learning method. We suspect that the reason is due to the fact that the supervised learning method fit too well to the training data. But then in the test scenario, the environment has changed a little bit. The number of people working in the office has been changed a little bit. So the supervised method does not work as well as the fingerprint-based method constructed based on unlabeled CSI data. Now, in the second scenario, we look at the case where we have an outdoor trajectory, and then we have a bunch of base stations, and we take the measurement using the SSB RSRP. So basically, we travel. We have a trajectory that travel along 2.6 kilometers, and then we also perform some data augmentation so that we get much more data for training and testing. Now it turns out that in this real data experiment evaluation, if we don't have a strip map, meaning I allowed my optimization variable to locate everywhere in the map without being restricted to the street, then we can achieve localization performance to about 90 meters. If we use a strip map to restrict the trajectory on the straight, we can further reduce the localization error to within 60 meters. So which is already pretty good because the measurement is very coarse, where we only measure the resist signal strength for a Y beam, which is a SSB beam. Now we can also demonstrate the construction of a MIMO map. So this corresponds to the CSI acquisition problem in FDD massive MIMO downlink, where we have a base station with many antennas, and we have a mobile, we have moving users, and then it is a difficult problem of an efficient estimation of the high dimensional CSI, right? So we try to build a radial map to map every position xi to the statistics of the high dimensional CSI. In particular, in this example, we try to use the covariance matrix of the MIMO channel as the so-called statistic of the CSI. So the goal here is to construct this covariance matrix map. And what we have is that we have the measurement as a sparse CSI measurement, where H is the full dimensional channel, and A is field pilots, right? So A is, for example, A is a sensing matrix with a number of rows much smaller than the number of the antenna. So YT is a sparse observation channel. So if we investigate the case where if we have just a few, if we have a sequence of sparse observation of the channel, how do we recover the location xt, and then by recovering the location xt to estimate the covariance matrix for every possible locations in the city. And the philosophy is the same. We formulate some Bayesian estimation problem, which allows us to jointly estimate the CSI, the position, and also the radial map, right? And then it turns out that indeed we can have the error on the covariance matrix estimation tends to a small number if we are given sufficient number of the measurements. Now we'll talk about more details on this topic in lecture 3.3 about blind CKM utilization. So here I just try to give you a rough idea that what we can do using this Bayesian framework. So here it comes to our final topic. How do we utilize the spatial regularization? So this is the scenario 2, where instead of having a sequential measurements, we have scatter measurements, right? This is due to the fact that in practice, the CSI measurement may not come in sequence. For example, CSI measurement can come from different users. And then, for example, one user make a phone call and then it goes offline, right? So measurement can be scattered without time sequential property. Now, what we do is that we do batch location recovery, which means that we are given a batch of measurements, and we try to recover the location. So for each location xi, we observe the CSI hi, right? We don't know xi. So by processing the larger amount of CSI hi, we try to recover the xi hat. Now, what we want to do is that we want to examine an approach that based on assumed property. Now, suppose that there exists a CSI distance metric, dhi xj, such that the distance between hi xj and the distance between the true location xi and xj has a linear relationship perturbed by some zero mean Gaussian noise. So this idea is similar to the principle of channel charting. As I mentioned before, the channel charting try to utilize the relationship that the closer the location, the more similar the two CSI, right? But here we try to investigate a stronger property that this relationship is linear up to some zero mean noise. So let's argue why it could be the case. So our argument will use the so-called quasi-specular environment model, where we consider that we have a transmitter. When the signal punch a reflector or a surface of a material, it will bounce towards a different direction, right? And then the strongest signal will follow the specular reflection property. But then there are also scattering propagation, where the reflected signal can go to the other direction. However, we assume that the scattered signal or the reflected signal will roughly contains in a limited angle range. So this is why we call it as a quasi-specular reflection. Now, with this understanding, then we can simplify the reflection propagation or scattering propagation as a line-of-sight propagation from a mirror transmitter. Now, for example, in this propagation path, it is the same as a propagation path transmitting from a mirror transmitter location towards the receiver following a straight line. And of course, due to the scattering, so the mirror transmitter may locate also so the virtual mirror transmitter may also locate in the neighborhood of the specular mirror transmitter, so like this. So same argument can be applied to diffraction, right? So the received signal of R1 can be understood as the received signal emitted from a mirror transmitter and then arrive at the receiver in a straight line. Now, the reason that we introduce this model is that we try to construct a so-called coherent patch to understand the similarity of the propagation environment within the neighborhood. Now, a coherent patch is defined as a small enough area where any 2 points, P1 and P2, share exactly the same propagation environment, as they are seeing the same visible transmitter mirror lattice. So an example is here. Say we have a transmitter here, we have a transmitter here, and we have a receiver here, right? We have a multiple path. We have a scatter path, which correspond to an equivalent virtual mirror of Tx at location A1, right? And then we have one reflection, a path with one reflection, which correspond to a transmission from a mirror location A3 directly to location Rx, right? We have also double reflection and triple reflection, which correspond to the transmission from these mirror locations. Now, if the environment is not that complicated, for example, it just consists of a small number of walls, then the received location may see just a finite number or a small number of virtual transmitter locations like this. And when you move from Rx towards its neighbor, it probably see the same set of virtual mirror transmitter location, the same set of this A1, A2, A3, A4. Now, if this is the case, then we say that the two receiver location are within a same coherent patch. Now, this is so we are not the first to invent this the concept, and this coherent patch concept has been utilized in many in ray tracing community for many years. Now, the good thing is that with this coherent patch model, we can construct a so-called theoretical matrix like this. Say we have a SISO OFDM channel H1 and H2 corresponding to two positions X1 and X2. And then we can first compute the correlation of H1 and F2. The correlation means the correlation among the subcarrier. Say H1M refers to the nth subcarrier of the channel. So we compute the correlation on the nth channel and sum them up and perform inverse Fourier transform of this the correlation, and we get the function Ru. And then it turns out that we can define the CSI distance metric as the maximum argument U, as the argument U that maximize this function. Now, the physical meaning of this function is that this is actually the the correlation function in time, right? Because our channel, our OFDM channel H is in the frequency domain, so we compute the correlation in the frequency domain and perform inverse Fourier transform. So we get the correlation in the time domain. So this CSI distance metric is trying to find the index that to give us the maximum time correlation between the two CSI measured at 2 points. So the good thing is we can establish some analysis and show that the CSI distance between H1 and H2 is roughly a linear function of the geographic distance between these two positions. And the leading coefficient is roughly the bandwidth divided by the speed of time. Now, the coefficient depends on the bandwidth because of the because can be interpreted as the time resolution of the CSI, right? Because the larger the bandwidth, the better time resolution we have. Now, with this, we can simply extend the metric into MIMO OFDM, which is simply to sum over all the antenna. Now, so this is a comparison between our metrics and the other metrics in convention. So if we use a L2 norm matrix, which means that we simply compute H1, the MIMO OFDM channel H1 minus H2, and take the Frobenius norm, then we'll have the CSI distance metric with the physical distance metric appear highly nonlinearly. But in our metrics, we see that indeed it follows roughly a linear relationship. So then it turns out that from our experiment, using this linear relationship, we can do better performance in recover the location, the CSI location labels as compared to using the conventional CSI metrics. So this leads to the second tool I would like to introduce, which is the spatially regularized Bayesian inference. The framework is similar to the previous one, except that we can impose a regularization using this prior information, where the CSI distance is the sum factor times the physical distance with variable xi and xj to be estimated, plus some disturbance, some Gaussian disturbance, where in this formula, the CSI, HIQ, HJQ are given from our measurement data set, and then xi and xj are something we want to solve. So at the end, we can formulate a Bayesian inference problem, and then to learn the model parameters, so which help us to recover the trajectory. So here is a demo in an indoor environment using a synthetic data set. So the construction of the cost function is similar to scenario 1, where we use the temporal correlation, where we formulate, where we try to formulate the joint probability of the CSI observation and the trajectory we want to recover. So this is to try to exploit the spatial correlation. And then we add a regularization term, where the regularization term we'll try to we'll try to minimize the distance between the CSI try to minimize the difference between the CSI distance and the distance of the estimated positions, right? So we will do this, right? And then this is simply a model that captures the Gaussian distribution like this, right? So this is just one example formulation. It turns out that there are possibility to fine-tune or to optimize the way you utilize this the prior information, right? You can do maximum likelihood kind of a regularization. You can also do other regularization. And with this regularization, we'll need to introduce an additional parameter eta. And it turns out that the performance does not it's not quite sensitive to the parameter eta. Now, of course, if you have some prior information to optimize the eta, then indeed we can find the best parameter eta to achieve the best performance. But as you can see from this figure, when eta range from 1,000 to 10,000, the performance is roughly similar. Okay, so we also tested on the real data, where in the real data set, the real data set is available here. And here we also develop a deep learning structure to utilize the to exploit the spatial regularization for recovery. And so let me just briefly go over the numbers. So in the proposed schemes, in the indoors scenario, we can achieve the mean position error to be less than 0.5 meter. But then as compared to conventional channel charting method, which utilize a different CSI distance metrics, the performance is different. Now, the title of this lecture also include how we would exploit the environment aware approach. So as we mentioned at the very beginning, we have generated approach that directly map the environment geometry to the CSI, to the radial map, right? So so if we have this capability, if we have built up this learning model, then it can also enhance the performance of the blind construction, right? The self-localizing radial mapping, in the sense that with the environment information, we can use deep learning to generate an initial the initial point or the initial radial map, right? And then with the initial radial map, we can run our Bayesian approach to achieve a better construction. Now, the reason behind this is the following. If we take a look at our Bayesian framework, the framework requires us to jointly estimate the CSI, the position, as well as the radial map, right? So this is more like a chicken and egg problem. We are given the radial map to recover the CSI and position. So put it this way, we need to rely on the radial map to recover the position and the CSI. And on the other hand, we need to rely on the position recovered CSI to update or construct the radial map. So this is a chicken and egg, and this problem is by nature ill-posed. In the previous step, the reason that we can solve this problem is because we have utilized some so-called anchor information due to our modeling here, where we establish the MIMO beam model. We have established a path model. So although this model just gives us a very coarse location information, but then this coarse location information, it turns out that suffice to leads us to a good local optimal when solving this ill-posed problem. However, if you know the environment and we have some method to map the environment directly to a good initial radial map, then we can speed up the convergence of our algorithm and then enhance the performance of this so-called blind construction of radial mapping. Okay, so with this, let me summarize. So it is critical to resolve the issue on the demand for location-based CSI data for CKM construction and evolution, right? The reason is we may not have a precise information of the environment, and the environment is changing, so we need to keep updating our radial map. And in this lecture, we simply focus on a particular methodology called self-localizing radial mapping, where we first recover the location labels from the CSI data and then recover the CKM from the location label data. We spent some time on the theory to explain why it should work. In a nutshell, it is because there's a hidden spatial temporal correlation in the data. And then we further improve the performance from the rough idea of the very original version of channel charting by discovering a good CSI metric, where in some strict restricted condition, we find that the CSI distance is proportional to the physical distance. And then we utilize the same principle as channel charting to recover the location while embedding high-dimensional CSI data to low-dimensional physical space. With that, we have introduced two tools. One is a Bayesian information framework to exploit the temporal correlation of the data if the data comes in sequence. And the second, we utilize a spatial regularization approach to exploit the spatial correlation from the scattered data. All right, let me stop here. It is my pleasure to share this information to you, and hopefully this can to raise your interest in this area about self-localizing radial mapping. Yeah, thank you very much, and I would like to take any questions.
Okay, thank you very much, Professor Chen, for the very interesting and comprehensive talk on blended CKM construction method. So we got a couple of questions. So the first question asked about the question is can the method, the self localization radial mapping, right? So can this method extract the characteristic beam space of the environment by learning from massive historical training data?
Yeah, I think it is possible, as we have demonstrated in one of the examples. So in this example, we try to recover the covariance matrix for each possible location. Right. So the idea is similar. We have a bunch of sparse CSI observation YT, and then we try to recover the associated location XT with YT, right? And then we can like collect all the associated YT for a particular location, a particular grid. Geographical cell to estimate the covariance matrix associated with that geographic cell. By recovering the covariance matrix, we can recover the so-called beam space. Now, of course, this beam space is abstract because it may not know the direct position, but this is one methodology. By recovering the covariance matrix, we can recover the beam space. The second one is the second method is that you probably need to utilize the anchor information. For example, you need to know where the position of the patient station is, and then we can construct a beam model. Right? We can construct a beam model as a function of the base station location. And in this beam model, we have parameter, for example, CQM, that gives us the direction of the beam. And this CKM is some unknown parameter that is jointly recovered by solving the Bayesian problem. So after the learning, we'll know the nth beam is pointing towards direction C. Right? So I think this is the second approach to recover the beam space.
Okay, thanks. So the second question is asked about the trajectory recovery. So the in the design, right? So both visiting order and the timing are generally unknown. So when processing such sequential RSS data, does the algorithm rely on the probabilistic model like hidden Markov models to capture the state transition between different regions, or does it utilize unsupervised methods like time series clustering to achieve the blind segmentation?
Yeah, I think this problem is about this region-based localization, right? Indeed, we don't know the timing that we entered a room or leave a room. So we would simply set a variable to estimate the timing. For example, we put a variable here. We put a variable to estimate this timing. So this is T1 that transfer from room 2 to room 3. And then we have T2 here and T3 here. So this problem is simply a segmentation problem where the variable are the boundary, the time boundary, right? T1, T3, T4, up to probably T9, right? And then so the optimization, the formulation is similar. So we also formulate something like this, but by performing some transformation, right? We will transform the problem into the case where we estimate those timing that transferring from one room to the other room.
So we need certain timing information, right?
Sorry.
So we need certain timing information, right?
Yeah, we need the timing information. Yeah, we need the time index for the measurement YT, right? We need we know that at the 10 o'clock we get one measurement, and then at 11 o'clock we get another measurement. So we need exactly the exact timing of the measurements.
Okay. Thanks. That's quite clear. And so the next question is about the CSI distance matrix. So constructing such matrix strictly proportional to physical distance is quite challenging. So in deriving this matrix, right, do we need to fully utilize the full dimensional complex CSI with both amplitude and phase information? So what kind of information
do
you use?
Indeed, we need to know the full CSI. Just like in the CISO case, we need to know the OFDM channel in complex with complex values. So we need to utilize both the amplitude and the phase. So here how it works, right? So it has the two complex channel. We compute the correlation, and then we compute inverse Fourier transform. So we get this complex correlation function. And then we try to maximize the amplitude of this correlation function. So the short answer is, yeah, indeed, we need to know the full channel.
Okay. We have another question. It's I think it's related to the future direction. So in the summary, it is described that the SORM as a decoupled two-step framework. From system architecture perspective, does the estimation bias in the first step cascade? Does the estimation bias in the first step cascade and amplify as the input noise during the second step of the CKM construction? So is there a future roadmap to adopt an end-to-end deep learning framework jointly optimizing the localization and mapping on the unified loss function?
Yeah, this is a very good question. Yeah, indeed, it is an open loop, right? If the first step goes wrong, then the error will propagate to the next step. And currently, the framework is open loop, and we don't know how to do to have a closed loop estimation. Yeah, indeed. Yeah, this is something we need to look at in the future.
Yeah. I think that's an interesting direction in the future. So I actually I have a question. So actually, when in some scenario, right? So here the blended CKM construction basically means the location of the user is unknown, right? But in some scenarios, actually we cannot get the accurate location of the base station or access point, right? So do you have any idea how to handle that kind of scenarios?
Yeah, this this makes the problem much more challenging. Yeah, maybe we can utilize some information from the environment. I don't know, just try to brainstorming any solution for that, right? Maybe the environment can help, right? Because in the end, the base station can have some location in the 2D space, right? So it is not that many possibility for that base station location. So probably if we get much more measurement data, right, we can somehow pinpoint the location of the base station. I'm not sure if that works, right? Because it is again a kitchen and egg problem. It is
Yeah.
but I'm not sure if we have enough science information. Probably we can do something. Either
So is it similar to in your problem? Actually, you have both location, also you have some parameter to estimate, right? Is it possible to put the, for example, base station location as another parameter to estimate?
I'm actually not optimistic to that because this is related to the channel charting problem that has been investigated for many years. In their problem, they don't need the position of the base station, so they can recover the physical space in a virtual space. So we can recover the trajectory in a virtual space. If you don't have any anchor information, so you may have scaling or rotation, maybe also have some translation, flipping, etc. So in the end, you still need to somehow utilize some anchor information to correct those rotation, scaling, translation. I don't know if we know the environment. For example, if we know here there's a obstacle and then there's a building, there's a ceiling. If we utilize those locations, perhaps we can bypass the demand of the anchor information. I'm not sure. Just yeah.
Okay.
Maybe we can like further look into that.
So for the last question, right? Can you turn to page 13?
Yeah.
Right. So so in this you have a measurement model, right? So this one, it looks to me like it looks like a stochastic channel model, right? So with some Gaussian distributed shadowing factor. So my question is, because when we use this model, this means that in the whole environment, right, the environment should be stationary. It has the same distribution, right, over the whole environment. So my question is, if the environment become super complicated, right? So if the assumption does not hold, so how to handle this case?
So I think there are two sets of things. One is if the environment is still static, is the model okay? Is the model precise? the model is not precise. The biggest issue is the randomness, right? Because throughout the discussion, we always assume zero mean, which means that this is Gaussian, and then so it is unbiased, and also the BIM model is unbiased. But in reality, it's not zero mean, right? It's biased. The mean is not zero. So this is the biggest issue, and this is why in our evaluation, if we use synthetic data, let's see, this is synthetic data, we can achieve a pretty good performance. But if we use real data, the performance degrades like by 2 times. So this is the reason, right? Because the disturbance is not zero mean, it's biased. The second level of your question is, what if the environment is not stationary? So if it is, so if the stationary is in time, right, then we can collect more data in the time and keep updating those parameters. So this is not an issue, I think. Now, if the stationarity is in space, then this is more complicated. We don't know how to handle that. Probably we need to make a more sophisticated model, but then this is trade-off, right? Because when your model becomes more sophisticated, then it's more difficult to acquire the correct parameters, right? So so I don't know. So this also, I think this also brings in a quite interesting direction. So in this model, there's no information, but there's no geometry information in the model. So if we have the geometry of the model, of the environment, probably we can like put this information into the measurement model to make it more accurate. So this probably what you mean by stationarity, right? Because if we have a building here, then we may have a different measurement model on the both sides of the building, right? So if we have some way to have some method to utilize this information, then we can probably do better.
Exactly. Yeah, that's quite interesting. Yeah. Okay. So due to time limitation, so we still got some other questions, but due to time limitation, we may have time to ask Professor Chen to answer the question during this online seminar. So actually, the questions will appear on the website of TaskPark. So we will also invite Professor Chen to take the questions there and have a discussion maybe offline there. Okay, so thanks Professor Chen again for the very interesting talk and a very insightful answering for all the questions. Okay, thank you again. Okay, thank you very much.
Okay, thank you everyone for your attention. Thank you.
Okay, so I think that's all for the talk today, and see you